Okay, so today's video is about explaining the proof of Ethos formula. Now, this is not something, I don't think it's as important as being able to apply Ethos formula, but I just want to demystify a bit the proof and the ideas of the proof. They're not hard, and even though Ethos formula, the first time you see it seems mysterious, the ideas are quite simple. All right, so it's very similar to the proof of the fundamental theorem of calculus, okay? And the main observation, the starting observation is that, okay, so let's say I'm on 0t, okay? And I do a partition of 0t, okay? Those are my tj's. And simple observation but powerful is that I can write ft minus f0, so how much my function vary, right, as the sum, telescopic sum of the increment. Very simple. And that's the power of calculus, that actually I can think of these increment as being as the tj is getting closer and closer, and so I can rewrite the increment as follows: as f prime tj times tj plus 1 minus tj. Okay? Now, this tj here, okay, so ft prime j minus, right, okay. So here I would have a perfect equality by the mean value theorem if I take a tj, there's a special tj, right, in between by the mean value theorem, where I have perfect equality. Now, I don't take this perfect equality. I rather just take tj, the tj at the beginning of my interval jj plus 1. But then I get an error, okay? But the error is the difference between the derivative at tj and that special tj bar times this, okay? Now, and this is just the mean value, yeah. So now what happens is when you take the limit n tends to infinity, this error tends to 0. So when you take the limit n tends to infinity, this part tends to the integral, because this is a Riemann sum, so I get the integral of f prime, okay? And what happens with the error? Well, the error is such that when I take the limit tj, when I take the limit when tj is really close to tj plus 1, all right, this term actually converges to 0, all right? So it's as if I get, if you want, the integral of something which goes to 0, okay? So this doesn't matter, okay? Again, the idea is what? Telescopic sum and Taylor's approximation and controlling the error. Same thing is true for Ethos formula, except that because we have a quadratic variation and a bounded variation, you have to go to second order. Okay, so let's just look at the proof that it's in the book, and we'll comment on it. Okay? Now, we need a second derivative here, remember, from the assumption. So I need to have two derivatives, and we'll assume that the second derivative is bounded, okay, for this proof. Okay, it holds even though the second derivative is not bounded, but let's assume it. You'll see why. Then you do the same idea, okay? That is, I can write fbt minus fb0, right? I can write this as the telescopic sum of my increment. I'm just rewriting it. And then the power of calculus enters. I think of tj very close to tj plus 1. Then I use Taylor, okay? I use Taylor on this guy, on this increment. So I get f prime of btj, beginning of the interval, the Bryan increment, because I expand around btj, okay? And then I go to second order, plus 1/2 f prime prime, btj, the increment square. Okay, so it's the second order Taylor approximation around BTJ. Okay, and then I have an error. Okay. Now, when n tends to infinity, we know this guy converges in L2 sense. That was the Ito integral. It converged to the Ito integral with the strategy f prime of bs. So that's my Ito integral in my in Ito's formula. The second term should converge to the Riemann integral, and you can expect that because BTJ plus 1 minus BT square is essentially like TJ plus 1 minus TJ. Not exactly equal, but we know, at least in terms of quadratic variation, that the quadratic variation of B is actually T. Okay? So what we're going to do is subtract what we want from this. And so this is what we get, right? So I subtract what I want. And we have to show that this goes to 0. And now the whole point is to realize that this calculation is very close with the calculation of quadratic variation. Okay, go back to it. So what you're going to have, okay, so you want to show that this goes to 0, right? So in L2, so there's a 2 missing here. I want to show that the L2 norm of this guy goes to 0. Good. So you expand the square. So when you expand the square, what happens, I get a double sum, okay, of these two guys. And then I have, so I want to show that this goes to 0. So I have the term where j is equal to k. What happens there, when j is, okay, so when j is smaller than k, what you do is the same trick that we did before. That is, you condition. So if j is smaller than k, you condition on tk. And what happens is that this guy gets out of the conditional expectation. This guy also, because it's ftk measurable. This guy happens before tk, so it gets out. And the only thing that remains is this guy. But this guy is the expectation of this given ftk is exactly that. Okay? It's the variance of the increment. This is independent ftk. So you get 0. Alright? So the only thing that matters exactly like the quadratic variation calculation is the term where j is equal to k. But when j is equal to k, okay, so if you want, you can condition on, you can either do the calculation explicitly like I do here, or also possibly you condition on oh no, you have to do the calculation. So you actually expand the square, all right? And now you're going to pick up the fourth moment of this guy, and then the mixed term, and this guy square. So you're going to get something exactly this. This is the fourth moment, right? And you do the cleaning of this, and you get that. Okay? Now this is why I want the second derivative to be bounded. So this guy is finite. Okay? There's a way to get out of that, but that complicates the proof. Now the sum of tj minus tj squared, that goes to 0. Because same thing as for the quadratic variation, I think can take the maximum of the time increment, okay, out of that sum, and then what I get is just the maximum out, and then the sum without the square, which is just t. And this goes to 0 because the partition will always assume that tj plus 1 minus tj goes to 0 uniformly. All right? Okay, so what's the point of the proof? Again, is that you do a Taylor expansion of the increments, f of the increments, but you do it to second order to pick up the quadratic variation, and then the calculation is very similar to quadratic variation. Now, I don't handle in this proof the error term, but it's a bit like in the fundamental theorem of calculus proof. The what you're going to get is essentially like a Riemann integral with something, with an integrand that goes to 0. So it goes to 0. All right. So the other thing I would mention is, what about when you have a function of time? The proof is exactly the same. That is, you do a Taylor expansion, okay, but in two variables. And now you're going to have also the dt's and the dt dbt, okay? Now, how do you get rid of the dt dbt, okay? So exactly like dbt square is the quadratic variation in this, guys, showing that the term dt dbt doesn't matter is about what we call the cross variation, okay? So that's actually a problem in the book, so let's just comment on this. So the cross variation of t and bt is a bit like the quadratic variation, except I just take the increment and I multiply by the increment of time. So we might see later the cross variation between two processes. Okay, so here my two processes are Brownian motion and just the function t. But I could possibly consider Brownian motion increment times the increment of some other process. Okay, so it's about essentially like the correlations between the increments of two processes. So this actually, if I take the time as a process, this is equal to 0, and this justifies the rule dt dbt is equal to 0. So why is that? Well, this convergence is in L2, so that means that the expectation square of that should go to 0. Okay, and so let's just do it. So the square of a sum, again, is a double sum. You have the sum where j is equal to k here, and the sum where j is not equal to k, say j is smaller than k, and do it twice. Okay? So what happens is that I get for j is equal to k, I get the time square, and I get the Brownian increment, but the Brownian increment square is just the time. So I get, if you want, the sum of tj plus 1 minus tj cubed, that we know is going to be small. We'll repeat that later. And then for the other term, it's even easier because, okay, I have the expectation of two increments, okay, that are not equal. So increments are always orthogonal. In fact, they're independent for Brownian motion. And this guy is equal to 0. So this variation, cross variation, is just sum over j, tj plus 1 minus tj cubed. But again, you can play the same trick, that is, take the worst increment out, the maximum, and let's say square, take the square out, and what you're going to have is just the sum of the increments without power, and this is the telescopic sum, and it gives me the last time which equal to t. So this goes to 0 when n tends to infinity, just because we assume that in the partition, the mesh, or the distance between 2 points, goes to 0 uniform. All right? So this is the idea behind Ethos' formula when t is equal to, when you have a function of t and bt. Again, you do a Taylor expansion, so you're going to pick up all the derivative, exactly like when you only have a function of bt. The only difference is that the cross term t bt, and what you're going to have instead of quadratic variation is this cross variation, and then if you do the proof, you realize it's equal to 0. All right? Okay. Thank you.